Hello and welcome everyone. I'm Lekha. Today I'm going to talk about system design in software engineering. Today's agenda covers several key topics in system design. Firstly, I'll talk about what is system design, what are requirement analysis, what is architectural design, high level overview of software design patterns, database management, fault tolerance, security, and case studies. What exactly is system design? System design is one of the important steps in software development lifecycle. It is the process of defining the architecture, interfaces, and data for a system that satisfies specific requirements. It is essential for creating robust, efficient, and scalable solutions that meets the needs of users, stakeholders, and the broader ecosystem. It involves a holistic approach that considers various factors including performance, reliability, security, usability, and cost effectiveness to deliver high quality systems that drive value and innovation. To design a system, first we need to gather requirements from various sources. Requirement analysis is a process used to determine the needs and expectations of a new product. It involves frequent communication with the stakeholders and end users of the product to define expectations and document all the requirements. There are two main types of requirements: functional and non functional requirements. Functional requirements are all about what a product must do and what its features and functions are. Non functional requirements specify criteria that are used to judge the operation of a system, like performance, reliability, scalability, availability, etc. Let's talk about some important non functional requirements. Performance can be measured by how quickly the system returns results. For example, the system's response time, such as processing 1000 requests per second. Scalability can be measured in terms of how performance changes with higher workloads. The system's ability to maintain performance under increasing workload, such as doubling the number of users without significant degradation. Availability can be measured by the average system downtime. The system's uptime and downtime, such as ensuring 99.999% availability annually. Reliability can be measured by how often the system experiences critical failures. The system's stability and robustness, such as experiencing critical failures less than once per year. Architecture is crucial in all engineering fields. In software engineering, it is the process of defining the overall structure and organization of a software system. Architectural patterns are reusable solutions to the commonly occurred problems. Key considerations in architectural design include balancing trade offs between different architectural styles, anticipating future changes and growth, and ensuring alignment with business requirements and constraints. Most common architectural patterns are model view controller architecture, microservices architecture, client server architecture, event driven architecture, etc. Let's look at model view controller architecture. MVC separates an application into three interconnected components: the model, the view, and the controller. The model represents the data and the business logic. The view presents the data to the user interface, and the controller handles user input and updates the data model and view accordingly. MVC allows code reusability and scalability. Microservices architecture has become widely adopted by tech companies in recent years. Microservices architecture breaks down applications into smaller, independent, deployable services. It enables agility, scalability, and easier maintenance. While architectural design focuses on high level decisions regarding the overall structure and organization of a system, design patterns address specific implementation level issues within that structure. Design patterns are reusable solutions to common problems that arise in software development. They provide a way to structure code in a way that is easy to understand and maintain, and they can be used to improve the overall design of a software system. Design patterns are divided into three categories: creational, structural, behavioral. Some examples of design patterns are singleton design pattern, adaptive design pattern, chain of responsibility design pattern, etc. In system design, database management plays an important role, offering the essential infrastructure and resources needed for efficient data handling. Through meticulous organization of data, ensuring its security and guaranteeing accessibility and reliability, database management underpins the functionality, performance, and scalability of software systems. Effective data management is indispensable in constructing robust and reliable systems that meets the demands of modern technology landscapes. Choosing the right database technology is critical considering factors like data volume, access patterns, scalability needs, and consistency requirements. Databases are classified into various types. Relational databases such as MySQL excel in structured data management and complex relationships. NoSQL databases like MongoDB offer flexibility for unstructured or semi structured data and horizontal scalability. In memory databases like Redis prioritize speed by storing data in memory, ideal for caching and real time applications. Time series databases such as Prometheus specialize in storing and querying timestamped data points, perfect for monitoring and analytics. Search databases like Elasticsearch provide advanced full text search capabilities vital for applications requiring robust search functionalities. Now, pause and think about this scenario where a critical system like a bank application crashes unexpectedly. What impact would it have on customers and business operations? Such an event could lead to a halt in essential services, disrupting customer access and potentially resulting in financial losses due to halted transactions or impaired revenue streams. Operational delays might happen, affecting project timelines and increasing overhead costs as efforts are redirected towards addressing the issue. Additionally, the company's reputation may suffer, with customers experiencing dissatisfaction. So, what can we do to resolve this issue? To avoid these kind of scenarios, we have to make sure our system is fault tolerant. Fault tolerance is like having a safety net for a system. It's the system's ability to keep working even if something goes wrong with its hardware or software. This is done by having backup systems in place, checking for errors, and automatically fixing them if they occur. So even if a part of system fails, it can still carry on functioning smoothly without causing any major disruptions. For example, load balancers. These distribute incoming requests across multiple servers to prevent overloading and ensure optimal performance. Load balancers detect and route traffic away from failed or underperforming servers, maintaining seamless operation. Security holds utmost importance in system design, encompassing elements such as authorization, authentication, data encryption, and network security. Authorization and authentication ensure only authorized users access resources, while data encryption protects sensitive information from unauthorized access. Network security secures the system's infrastructure against external threats. These measures collectively fortify the system, mitigating risks and safeguarding against unauthorized access or data breaches. Now, let's explore a real world case study of system design for a video sharing service leveraging the microservices architecture. At the forefront are the clients, including web and mobile applications, which interact with the system through an API gateway. This gateway serves as an entry point, routing requests to the appropriate backend services and managing authentication and authorization. We have two microservices in this architecture, which are user service and video service. Load balancers are strategically positioned to distribute incoming traffic across multiple instances of the video service and user service, ensuring optimal performance and reliability. The video service manages video content and metadata, handling uploads and storage, while the user service oversees user data, authentication, and profile information. Both services interact with dedicated databases to efficiently store and retrieve video data and user information. For video and user metadata, we can use relational databases like MySQL. Object storage services like Amazon S3, Google Cloud Storage, or Azure Blob Storage are typically used for storing the actual video files. Through seamless integration of these components, the system efficiently handles users' requests, deliver high quality video content, and provide a seamless experience to millions of users. As we conclude our presentation, I would like to thank you for your participation. While there are numerous aspects to consider in system design, I have highlighted key elements that I believe are essential. I hope it has provided valuable insights into the intricacies of system design.